Finding lengths of vertical and horizontal line segments. This is a concept that will help you to find the area between two curves, as well as find the volume of a solid of revolution. So it's very important that you understand this concept because it will help you with those topics that we'll be doing in the next few days. So number one, find the length of each vertical line segment. So the main thing that you need to understand here is this. So for example, suppose we have this particular vertical line segment. We can just see how long this line segment is by counting on our graph. We can see that it's 1, 2, 3 units long. And this one here, we can see that it's 2 units long. And this one here, we can see that it's 1 unit long. The important observation that we want to make here is that for this line segment whose length is 3 units long, observe that the y-coordinate of the top endpoint is 3, and the y-coordinate of the bottom endpoint is 0. And if you do 3 minus 0, you get 3, which is the length of the vertical line segment. The same holds true for the other two vertical line segments. This one here, if you look at the y-coordinate of the top endpoint, it's 2. The y-coordinate of the bottom endpoint is 0. And when you subtract the y-coordinates of the top and the bottom endpoints, you get 2 minus 0, which is equal to 2. That's the length of this vertical line segment. And also, we have the same thing here. 1 minus 0 will give us the length of the first line segment that we have, which is 1. So what we observe is that we can find the length of a vertical line segment by looking at the y-coordinates of the top and the bottom endpoints and then subtracting them in the order top minus bottom. So now we move on to number 4. Number 4 is related to number 1, and it's for us to be able to generalize our observations from number 1. And why do I say that? Because in number 1 we worked with 3 specific vertical line segments. So the first vertical line segment was located at x is equal to 1, the second one at x is equal to 4, and the third one at x is equal to 9. So we had 3 specific vertical line segments whose lengths we found in number 1. What's number 4 about? Let's see if we can do it for an arbitrary vertical line segment. So you see the red line segment that I just drew. It could be anywhere between the graph of y is equal to the square root of x and the x-axis. I just happen to have drawn it in that particular place. So where it is indicated by the x-coordinate of either the top or the bottom endpoint. And it's the same x-coordinate for the top and the bottom endpoints. So for example, if x is 1, we'd have this one. If x is 4, we would have the second one that we worked with in number 1. And if x is 9, we would have the third one that we worked with in number 1. But x could be any value. It could be 1, it could be 4, it could be 9, or it could be something like 5 or 7.5, or even an irrational number like square root of 2. So now we have an arbitrary vertical line segment. So can you write a function of x? In other words, a function of its location. Can you write a function of x that would give us the length of this vertical line segment? And the answer is yes. And how would you do this? You would do this by taking your observation from number 1, in which you found the lengths of the 3 vertical line segments that were given, simply by subtracting the y-coordinates of the top and the bottom endpoints. So we should do the same thing for an arbitrary vertical line segment. We should subtract the y-coordinates of the top and the bottom endpoints. So our function of x that would give us the length of an arbitrary vertical line segment between the graph of y is equal to square root of x and y is equal to 0 is f of x is equal to the square root of x minus 0, top minus bottom. Of course, you can simplify that to f of x is equal to just the square root of x, and you can test this out. Here's what I mean by that. Check to see if it works for the 3 vertical line segments from number 1. So for the first vertical line segment, x is equal to 1. So if I substitute 1 for x in this function, I get f of 1 is equal to the square root of 1, which is 1, and that's the length of this vertical line segment. If I substitute 4 for x, then I would be looking at the second vertical line segment from number 1, and I'd have f of 4 is equal to the square root of 4, which is 2, and that's the length of this vertical line segment. And if I substitute 9 for x, I'd be looking at the third vertical line segment from number 1. So I'd have f of 9 is equal to the square root of 9, which is 3, and that's the length of the third vertical line segment from number 1. So what we have accomplished in number 4 is we have managed to write a function of x that would give us the length of an arbitrary vertical line segment between the graph of y is equal to square root of x and the x-axis. So now that it's a function of x, I could have a vertical line segment anywhere between the graph of y is equal to square root of x and the x-axis, and I'd be able to find its length. Now we move on to number 2 and number 5. So number 2 says, find the length of each horizontal line segment. Just like we did for number 1, we could simply count because our horizontal line segments are drawn on this set of coordinate axes on graph paper, and we can just count. Like for example, this one here has a length of 1. The second one that I'm looking at now has a length of 1, 2, 3, 4. And the last one here has a length of 1, 2, 3, 4, 5, 6, 7, 8, 9 units. The observation that we want to make is that we can find the length of each horizontal line segment not just by counting, but also by looking at the x coordinates of the right and the left endpoint. For example, for the third horizontal line segment, you can find that its length is 9 by subtracting the x coordinates of the right and the left endpoints. 9 minus 0 is equal to 9. And you can make the same observation for the other two horizontal line segments, like this one here. If you subtract the x coordinates of the right and the left endpoints, 4 minus 0 is equal to 4. And that's the length of that horizontal line segment. And this one here, 1 minus 0 will give you 1, the length of this horizontal line segment. So how can we generalize? That's what number 5 is about. Here's what we've observed in number 2. To find the length of a horizontal line segment, what we have to do is we have to take the x coordinate of the right endpoint and subtract from that the x coordinate of the left endpoint. So let's see if we can do that for an arbitrary horizontal line segment. First of all, how do we indicate where our horizontal line segment is, where our arbitrary horizontal line segment is? And to understand how we do that, you can look at the 3 horizontal line segments that were shown in number 2. You can make the observation that the location of a horizontal line segment can be indicated by looking at the y coordinate of an endpoint. So for the short one here, both endpoints have a y coordinate of 1. And for the longest one, both y coordinates are 3. So the y coordinate of an endpoint will tell us where our arbitrary horizontal line segment is. So if y is 3, we're talking about this one. If y is 1, we're talking about the short one at the bottom. But let's just keep y a variable so we can talk about an arbitrary horizontal line segment, one that could be anywhere between the graph of the given function and the y-axis. And because the location of our arbitrary horizontal line segment is given by y, we need to write a function of y that will give us its length. So we need to rewrite the x coordinate in terms of y. So how do we do that? Well, for this curve, it is the graph of y is equal to the square root of x. So you need to solve that equation for x by squaring both sides. So we get x is equal to y squared. So any point that's on the graph of y is equal to square root of x will have an x coordinate that can be written as the square of its y coordinate. The left endpoint is easier to work with. Y is just y. It's arbitrary. And no matter what y is, because it's always going to be ending on the y-axis, the x-coordinate will be 0. So we take our observation from number 2, and we know what to do. To find the length of an arbitrary horizontal line segment between the graph of y is equal to square root of x and the y-axis, what we have to do is like what we did in number 2. We would take the x-coordinate of the right endpoint, we would take the x-coordinate of the left endpoint and subtract them in the order right minus left. So our function is f of y is equal to y squared minus 0. And if you simplify that, you get f of y is equal to y squared. So now we can test it out. Going back to number 2. This short horizontal line segment is located at y is equal to 1. So what is its length? Well, according to our function here, f of 1 is equal to 1 squared, which is 1. The medium length horizontal line segment is located at y is equal to 2. What is its length? F of 2 is equal to 2 squared, which is 4. And that's the length that we found for that segment in number 2. And the longest horizontal line segment in number 2 was located at y is equal to 3. What is its length? According to our function, f of 3 is equal to 3 squared, which is 9, and that was the length of our longest horizontal line segment from number 2. So what we have here is a function of y that would give us the length of a horizontal line segment between the graph of y is equal to square root of x and the y-axis, no matter where that horizontal line segment is located. Now we go on to number 3. Find the length of each vertical line segment. And again, just like we did in number 1, we could simply count 1, 2, 3, 4, 5 for the length of the first vertical line segment between the two graphs. 1, 2, 3 for the length of the second vertical line segment between the two graphs, and 1 for the length of the third vertical line segment between the two graphs. But where is each one located? This one is located at x is equal to 1. This one is located at x is equal to 4. And this one is located at x is equal to 9. So we want to make the same kinds of observations that we had made earlier. Like we saw in number 1, to find the length of each vertical line segment, we could take the y-coordinate of the top endpoint and subtract from it the y-coordinate of the bottom endpoint. 6 minus 1 is 5. If we do that for the second line segment here, 5 minus 2 is 3. And if we do it for the third vertical line segment here, 4 minus 3 is 1. So what is number 6 about? It is about taking our observations from number 3 and generalizing them to an arbitrary vertical line segment between these two graphs. And again, by arbitrary, we mean it could be anywhere between the two graphs. So in number 3, we were looking at 3 specific vertical line segments between the two graphs. The first one was located at x is equal to 1. The second one was located at x is equal to 4. And the third one was located at x is equal to 9. So now we're looking at this arbitrary vertical line segment between the two graphs. Its location is given by the x-coordinate of either the top or the bottom endpoint. And to find the length of it, we're going to do the same thing that we did in number 3. We're going to subtract the y-coordinates of the top and the bottom endpoints in that order, top minus bottom. So our function of x that would give us the length of an arbitrary vertical line segment between the two graphs in number 3 would be f of x is equal to the y-coordinate of the top endpoint minus the y-coordinate of the bottom endpoint. And so we have f of x is equal to negative square root of x plus 7 minus square root of x. And when you combine the two radical expressions, you get negative 2 square root of x plus 7. And let's test this out for the 3 particular vertical line segments that we looked at in number 3, where x was 1, 4, and 9. So when I substitute 1 for x, I am looking at this vertical line segment, and I will have f of 1 is equal to negative 2 times the square root of 1 plus 7, which is equal to 5. When I substitute 4 for x, I would have f of 4 is equal to negative 2 times the square root of 4. Square root of 4 is 2. 2 times negative 2 is negative 4. Plus 7 is 3. And when I look at this one, x is equal to 9, and this function tells me that the length of this particular vertical line segment at location x is equal to 9 is negative 2 times the square root of 9. Square root of 9 is 3. 3 times negative 2 is negative 6. Plus 7 is 1. So in conclusion, being able to write functions of x or y that would give us the lengths of arbitrary vertical and horizontal line segments is an essential skill that you need to master to be successful with the topics in this chapter, which are about finding the area of a region between curves, finding the volume of a solid of revolution, and finally finding the volume of a solid constructed on a base with known cross sections.